afternoon, everybody. My name is Jaime Not. I go by Jaime. It's my honor to introduce Fitsum. He's my PhD student. He's been doing his PhD since spring 2021, but he joined my lab in fall 2019 as a visiting scholar. Before that, he has a bachelor in Ag and Biological Engineering from Aroma University in Ethiopia and master's from Banras Hindu University. I don't know if I pronounced that correctly, from India. He was working as a lecturer and researcher at Wardam Malabo University in Ethiopia. Fitsum's PhD dissertation research focuses on understanding evapotranspiration and soil moisture dynamics at field scale from vegetable crops. He employs different data from ground, above canopy sensors, UAV systems to develop data-driven decision support tools for agriculture and water management. So far, it's a little bit almost 4 years since we have been here. He has published 13 peer-reviewed articles. 4 of those 13 are, he was a lead author, first author. 4 of them are from his PhD dissertation. He has co-authored 2 extension factsheets, 3 conference proceedings, and he has given several conference presentations at different conferences. And this year alone, he got 2 awards for his oral presentation at the American Society of Agricultural and Biological Engineers from the Florida section and from the international meeting in Omaha, Nebraska. He's working hard to finish his PhD, and he's on track to finish in summer 2024. So with that, I will leave the floor to Fitsum.
Thank you so much, Dr. Hyman, for the nice introduction. So as Simon said, my name is Fitsum Teshome. I'm a member of the Water Resources Research Group at the Tropical Research and Innovation Center. And today I'm here to give presentation on my research project. And the title of my presentation is Leveraging Ground and UAV-based sensor data, cross simulation models, and AI for agricultural water management. So without further ado, I'll jump to my presentation. So this presentation has 4 sections. In the first section, I'll talk about the general concepts, problems, and the hypotheses related to our research project. In the second section of this presentation, I'll talk about the main and the specific objectives which are related to our research project. And in the third section, I'll talk about each chapter of my research project. And finally, I'll conclude my presentation by giving some remarks on the key findings of our research project. With that, I'll go to the introduction. As you all know that agriculture is the main consumer of freshwater resource. It consumes around 70% of freshwater resource globally. And in United States, similar pattern is observed where United States agriculture consumes around 42% of water resources. And this sector is also known for consuming a significant amount of groundwater withdrawal. For instance, globally, it consumes around 40% of groundwater withdrawal. And in the United States, the number is more, where United States agriculture consumes around 60% of groundwater withdrawal. And this high water usage or withdrawal comes with consequences. For instance, it might cause water scarcity for other sectors, such as municipal, industry, even for the agriculture itself. And it also causes aquifer contamination and other, because if we are using too much water, we are going to have leaching, and that leaching might affect the surrounding environment like lakes and rivers. In addition to that, high amount of water usage in agriculture also causes high energy use in agriculture, and this also affect the environment due to pollution. In addition to that, it forces growers to spend more money on energy. But at the same time, we need more water to produce more food for the world's growing population. For instance, in next 25 to 30 years, we need 19% of more freshwater resources in order to feed world's growing population. However, the quantity and the quality of freshwater resources declining time to time. So we need a solution to balance this water demand and with the food supply. So in order to do that, what we have to do is we have to reduce the amount of water we use in agriculture. And one of the methods we can do that is efficient water management. We have to practice efficient water management, and this management can help us to reduce the amount of water we use in agriculture. For instance, some of the efficient water managements are precision irrigation. For instance, if we have a precision irrigation, we can control or we can apply the right amount of water at the right place in the right time. In addition to that, we can also practice deficit irrigation, where the amount of water we apply is less than the 100% of water requirements. However, in order to have efficient water management, we need to have a reliable data. Without reliable data, we cannot achieve efficient water management. And in this regard, digital technologies are transforming the way we collect data in terms of frequency and reliability. For instance, drones, drone-based sensors, AI models, and crop simulation models are helping us to collect important information that can help for efficient water management. So digital technologies can improve the water management via enhanced data collection, analysis, and visualization, because we cannot manage what we cannot measure. In order for us to manage our water resources or any resource, first we have to measure it and analyze it. But in this regard, agriculture lags behind in adopting these technologies for efficient water resource management. So only few studies have explored these digital technologies for agricultural water management. So in this study, we utilized ground and UAV-based sensors data to evaluate effectiveness of simulation models for agricultural water management in South Florida. So the main objective of this research project was to evaluate soil hydrology model effectiveness in improving agricultural water use efficiency in South Florida. And in order to answer this main objective, we formulated around 5 specific objectives, and I'll go through each objective in the coming slides. So this is our research project. In this research project, we have grown a sweet corn and green beans on 32 plots under 4 irrigation treatments and 4 applications. And our experimental design was RCBD. We used 16 plots for green beans crop, and we used 16 plots for a sweet corn. And we conducted this research project during winter dry season because it's an irrigation experiment. We don't want the rainfall affects our irrigation treatment. That's why we conducted this research project during winter season, and we conducted this research for 2 seasons for this project. And we had 4 irrigation treatments. Our irrigation treatments were 100%, 75%, 50%, and 25% full irrigation. And we calculated full irrigation by considering maximum allowable depletion, which is 50% of available water, which is the difference between fill capacity and the permanent wilting point. For this research project, we use linear mode sprinkler irrigation system, which is equipped with variable technology. This technology gives the irrigation system the capability to distribute different amount of water at different across and along the field. Let's talk about the weather of our experiment site or our homestead. So winter season is a dry season in a homestead. It's only received 8% of annual average rainfall, which is 1,400 millimeters. That's why we are conducted our research project during this period. And November, December, January, and February are the months which are included under winter months. And this, as you see on this figure, this month received less rainfall compared to the other months in this region. Obviously, this month also receive less minimum or annual average temperature compared to the other months of the year. And in South Florida, we have very unique soil, which is called chrome soil. This soil is very shallow soil. It's only 18 centimeter depths. And this soil also has high pH and high gravel content. Actually, the gravel content is more than 50%. And this soil is also known for low nutrient and water holding capacity. And because of that, frequent irrigation and fertilizer application is must to have optimum production. In South Florida, we have also very unique hydrology, and Biscayne Aquifer is the main source of water for agriculture, not only for agriculture, even for municipal. Biscayne Aquifer is the main source of water. But this aquifer is very close to the surface, and due to that, it's easily susceptible to saltwater intrusion and contamination. For instance, if you see this figure on the right, the red line is the freshwater saltwater interface during 2011. And if you see the green one, that's the interface during 2018. So this interface is moving more inward to the mainland. This is also because of saltwater intrusion. Excessive water pumping is causing the saltwater intrusion, and the interface is moving more to the mainland. But I'm not saying this is happening only because of saltwater intrusion. There are also other causes for this saltwater intrusion in the area. Okay, let's talk about data we collected in this experiment or in this research project. We collected UAV imageries using DJI matrix drone. And in addition to the drone, we also use Xenon's XT2 sensor and Radix MX sensor for UAV image collection. As you see on this figure, this Radix image and the thermal image is actually from Xenon's XT2 sensor. And in addition to the UAV image for the green beans and the sweet corn, we also collected the artificial reference surfaces that imitates the non-transpiring and fully transpiring plants. We needed this kind of temperature to calculate crop water stress index. I'll talk about this in last chapter of my research project. And we also collected above canopy temperature of green beans and the sweet corn using ground-based IRT sensor. And this is the configuration for our IRT sensor. That yellow one is the coordinator, and this green one is the repeater, and these blue dots are the IRT sensor. So the IRT sensors collect the canopy temperature of green beans and the sweet corn and transfer this data into repeater, and the repeater receives the information and send it to coordinator, and we download the data from the data logger at the coordinator. And this is when we are installing the IRT sensors before the experiment. And this is the configuration of our IRT sensors on the experiment side. And we also collect the soil hydrology components in this research project. We use terrestrial soil moisture sensors for monitoring the soil moisture content of our experiment sites. And we also use valley weather station and the power homestead station to collect weather parameters of our experiment site. And we also used lysimeter to collect the depopulation below the root zone using lysimeter. As you see here, these are our lysimeters, and these are the process that are involved when we were installing our lysimeters. And this is after installing the lysimeter. These two pipes are the one we use to extract or to pump out the amount of water stored in the lysimeter. And these are some of the softwares we use for our analysis. And in addition to these softwares, we also used Hypergator supercomputer computational resource for our analysis. And as I was mentioning before, in this experiment site, our irrigation system was equipped with VRI technology. So this technology gives the irrigation system the capability to distribute different amounts of water across the field. How this VRI technology controls the irrigation system, it's controlled the sprinkler and the speed, the linear speed. For instance, if you want to apply 50% of irrigation, what the VRI do, it controls turn on and off the irrigation sprinkler every 30 seconds. And by doing that, it applies only 50% irrigation application. For instance, if you want to apply 150, what the VRI technology does, it's allow the sprinkler to be turned on the whole time and delay the linear speed by 50%. By doing that, it applies 150% irrigation application. In our case, we had 4 VRI technologies in our irrigation system, and each VRI technology controls 2 zones, and totally we have 8 zones for our experiment. For the irrigation treatment, how we decide the time and the amount of irrigation we apply, we closely monitor the soil moisture content of the full irrigation, and when the average soil moisture content of the full irrigation reaches to the maximum annual depletion, which is the 50% of available water content, we started our application at that time. In order to decide the amount of water we should apply for the full irrigation and deficit irrigation treatments, we used equation 2. We subtracted the soil moisture content, average soil moisture content from field capacity, and then we multiplied that by root depths. And then we calculated the amount of water we should apply for full irrigation treatment. And how we calculated for the deficit irrigation treatment, we multiply this full irrigation treatment by fraction. For instance, if we want to apply irrigation amount for 25% irrigation treatment, we multiply the full irrigation by 0.25. And if we want to apply for 75, we multiply the full irrigation by 0.75. In this experiment, we also collected agronomic and phenology data. We collected plant height, canopy widths, fresh biomass bi-weekly, and we also collected yield and biomass at the end of the experiment from the 2 inner rows, as you see on this figure. We neglected all the outer rows in order to minimize border effects. So if I say this much about our project, let's jump to the first chapter of my research project. The first chapter of this project had one objective, that was also to evaluate the effectiveness of combining UAV imaging with machine learning techniques for the sweet-borne phenotyping. You might ask why this is important. Advanced phenotyping can help us for different purposes. For instance, you can use it for crop monitoring, you can use it for crop management as well as for yield prediction. Let us talk about how crop phenotyping can help in crop management. For instance, if you have different fertilizer applications or irrigation applications, by daily taking the drone image, you can see that how the crops are responding to different types of either irrigation management or fertilizer management. So by analyzing the drone image, you can see that the crops are responding either in good way or in bad ways for that particular irrigation or fertilizer application. In addition to that, we can also use plant phenotyping for yield prediction before final harvest. And then we can use this yield prediction for either for sale or for insurance purposes. So that's why we are interested to investigate UAV imaging and machine learning techniques for sweet-borne phenotyping. And the result of this study already published in the Journal of Computers and Electronics in Agriculture. You can use this QR code if you are interested in our paper. So for this study, what we did, first we generated the DSM and DTM using UAV image and the fixed body mapper. Then we subtracted the digital train model or DTM from the DSM to get the crop height or the crop surface model. Afterward, I will call it UAV image estimated height. Then once we calculated the UAV estimated plant height, we try to see the correlation with the measured data. Once we know there is a good correlation with the measured data, we use this UAV image estimated plant height, actually the 60%, to develop linear relationship between UAV image estimated plant height with biomass as well as with yield. And once we know there is a good linear relationship between these two variables, we use the remaining data to predict biomass, and the yield. In this study, we also generated 8 vegetation indices from the image, and then these are the 8 vegetation indices we generated using drone image. The first index we calculated for this analysis is NDVI. How you can calculate NDVI? You can subtract the red band from near infrared band and then divide that by the sum of near infrared band plus red band. For instance, if you see this figure, this is the NDVI value for one of the flights, and it ranges between 0.7 and the minus 0.6. Actually, NDVI range between -1 and 1. -1 is for very stressed plant, and 1 is for healthy plants. We also trained 5 machine learning models. We used 2 linear machine learning models and 3 non-linear machine learning models. And we used vegetation indices and very estimated plant height to evaluate the performance of the machine learning models for biomass prediction. And we only used vegetation indices to evaluate the performance of machine learning models for plant height prediction. So for the result, we observed that the crop surface model was able to accurately simulate the sweet corn plant height during different flights, and the distance for different flights ranged between 0.7 and 0.9, and the mean scale error ranged between 1 and 12 centimeters. We also try to see the correlation between combined plant height, measured plant height, and estimated plant height. And then we observed that there was a good correlation between combined measured plant height and the combined estimated plant height. Actually, the distance was almost 100%, and the mean absolute error was only 5 centimeters. Then we also observed that there was a significant linear relationship between varying estimated plant height with biomass and yield. And then once we know there is a significant relationship or linear relationship, we use that model to predict biomass and yield. And we observed that there was a good correlation between measured and estimated total fresh biomass and the total dry biomass. In addition to that, we also observed that there was a good correlation between estimated and measured fresh stem and freshly biomass. And we also observed that all the machine learning models were able to accurately simulate the plant and the biomass of the sweet corn. However, the nonlinear models performed better than the linear models in predicting biomass. And we also observed that the linear models performed better than the nonlinear models for plant height prediction, and the data scale for these models were 0.81 and 0.79 for these two models, and the root mean scale was 2.2 centimeters. So as a conclusion, integrating these two technologies, imaging and machine learning techniques, can significantly improve plant phenotyping accuracy and efficiency. So these findings have important implications for future plant breeding and crop management as they provide effective and non-invasive phenotyping. However, further studies are needed to refine these techniques' accuracy and explore their potential for real-world application. With that, I'll end chapter 1 and let's directly jump to chapter 2. Chapter 2 of this research project had 2 objectives. The first objective was to investigate the response of green beans in the sweet corn to different irrigation treatments. And the second objective was to evaluate the performance of DSAP model in simulating growth and yield responses to irrigation treatments. Why we are interested on these objectives as I was telling you before, we need efficient water management. However, there are different methods to achieve this efficient water management. One of the methods is deficit irrigation. Deficit irrigation is water management practices where you apply this amount of than the 100% crop water requirement, but we cannot randomly apply deficit irrigation. We have to first monitor how crops are responding to different level of deficit irrigation. Are they tolerant to some level of crop water stress? If they are stressed, then we apply the deficit irrigation treatment. So that's why we are interested to see how plants are responding to different types of irrigation treatments. However, there are different methods to to evaluate the crop tolerance to different irrigation, deficit irrigation treatments. One, we can do experiment. By doing experiment, we can evaluate crop tolerance to different irrigation treatments, or we can also use crop simulation models for investigating crop tolerance to different deficit irrigation treatments without having a field experiment. And the result of this study also already published in the Journal of Agricultural Water Management. And then you can use this QR code if you are interested in our research paper. So for this chapter, what we did, we used DSAT crop grow model and DSAT series model for simulating green beans and the sweet corn yield and the yield components. For DSAT model, we need daily weather data, soil data, and the crop management to calibrate the genetic options. Once you calibrate your genetic options, you can use that model to predict your yield and yield component, and then evaluate your model with the measured data. And if your evaluation result is good, you can use that model for predicting other season data. So for this study, we use blue coefficient estimator and the sensitivity tool to calibrate our genetic options for those models. And then we use the first season data to calibrate the model, and the second season data for evaluating the model. In this study, we also calculated water conservation and water productivity, water conservation due to deficit irrigation treatments. And then we also calculated water productivity of each irrigation treatments using equation 1 and equation 2. We also did ANOVA analysis, try to see if the irrigation treatments are affecting the biomass in the fresh yield. So for the result, we try to see how the irrigation is affecting the yield and yield components. And then we observed that the full irrigation treatment had a slightly higher fresh yield than other treatments during both periods and for both crops. And we also observed that the second season fresh yield, average yield was better than the first season yield for both crops and seasons. However, the irrigation level had no significant impact on the fresh yield at 90%, 95% confidence level for both seasons. Then we evaluated the crop grow green beans model for simulating green beans biomass and yield. And that the result has shown that this model was able to accurately simulate the biomass. For instance, if you see the mean absolute error during the evaluation period, it was 0.24 gigagram per hectare. And this model calibration period performance was better than the evaluation period performance to simulate the fresh yield. For instance, if you see the restart during calibration period, it was 0.77, and during evaluation period, it was 0.53. However, this model was able to accurately simulate canopy height and width with good accuracy during both seasons. And then we evaluated the sweet corn model for simulating the sweet corn biomass and yield. And we observed that this model was able to accurately simulate biomass and fresh yield with good accuracy. If you see the D-stat for the biomass, it was 0.89 during calibration period, and it was 0.997 during the evaluation period. And the same performance was observed for fresh yield prediction, where the D-stat was 0.9 for calibration period, and it was 0.82 for evaluation period. And this model was also performed accurately for simulating plant size, the sweet corn plant size. So for the water conservation, we calculated the amount of water conserved by each irrigation treatment, and we observed that the deficit irrigation treatment had higher water conservation compared to the other irrigation treatments. For example, if you see the first season data, you can see that the 25% irrigation treatment had saved around 1,000 meter cube of water per hectare for green beans and around 1,500 meter cube of water per hectare for a sweet corn. And then the same results were observed in the second season, where the 25% irrigation treatment had saved a significant amount of water for green beans as well as for a sweet corn. Then we calculated the water productivity from each irrigation treatment, and we observed that the deficit irrigation treatment had higher water productivity compared to the full irrigation treatment. For instance, if you see in the first season, the 25% irrigation treatment water productivity was 28.6 kg per meter cube for green beans, and it was 40.4 kg per meter cube for a sweet corn. And we observed similar result during the second season, where the deficit irrigation treatment had higher water productivity compared to the full irrigation treatments. So as a conclusion, deficit irrigation could be effectively used in South Florida as an irrigation water conservation strategy, and the DSAT model is a useful tool for crop management and decision making related to agricultural water management. So with that, I'll in chapter 2, let's jump to chapter 4 and chapter 3. So this chapter, chapter 3, had one objective that was also to accurately simulate evapotranspiration and the soil moisture content of green beans and the sweet corn using DSAT model. So while we want to accurately simulate evapotranspiration and soil moisture content using DSAT model, as I was telling you before, in order to practice efficient water management, we need data. What kind of data? Soil moisture data, and evapotranspiration data. One of the methods we can get those data are by doing experiments. But experiments are very expensive as well as they are time consuming. So what we did, we considered crop simulation model for simulating this soil hydrology components, such as soil moisture content and the evapotranspiration data. So this crop simulation model can simulate these two variables without intensively investing in sensors and the field experiment. The first thing we did for this one is we calculated crop evapotranspiration of green beans and the sweet corn using a standard method of soil water balance approach. This is the equation for soil water balance approach. We had measured precipitation, irrigation, soil water change, and percolation data. Then we used this measured data and calculated evapotranspiration for green beans and the sweet corn. However, in our experiment, during our experiment, the dosimeter were mostly unfilled, but we calculated the evapotranspiration using available percolation data, and then we observed that there was a poor agreement between measured and estimated evapotranspiration data. So once we know there is a poor agreement between estimated and simulated evapotranspiration, what we did, we found another method to calculate evapotranspiration, that's soil moisture approach. What we did for this one, we subtracted the previous day soil moisture content from today or current day soil moisture content, and we created a time series of soil moisture change, and we plotted that against time, as you see on this figure, and we segregated the wet period and the dry period. In this wet period, we assume that there is going to be a depopulation, but we don't have the depopulation data. We only consider the dry period to calculate evapotranspiration, and then we used equation 3 for calculating evapotranspiration of the green beans and the sweet corn. So now we have measured evapotranspiration data or estimated evapotranspiration data and measured soil moisture data. So we want to compare how the simulated evapotranspiration and soil moisture content is correlated to measured evapotranspiration and soil moisture content. So we used previously calibrated, we already calibrated DSAT model during chapter 2. So we used those models to simulate soil moisture content and evapotranspiration of green beans and sweet corn. How DSAT model simulates evapotranspiration? It simulates by following two steps. First, it calculates reference evapotranspiration by using either Priestley-Taylor method or Powell 56 payment method. Then after calculating reference evapotranspiration, it considers the leaf area index and the energy extinction coefficient to classify this reference evapotranspiration into reference evaporation and the reference transpiration. And then the second step, by considering the crop limitation, it reduces the reference transpiration into actual transpiration. And by considering the soil limitation, it reduces the reference evaporation into actual evaporation. So once we have actual evaporation and the actual transpiration, by summing two, we'll get actual evapotranspiration. And how this model simulates soil moisture content. First, it's considered USDA curve number to calculate runoff. Then once the runoff is calculated, that is assumed that rainfall plus irrigation minus runoff, it will give us infiltration. And that this model also assumed that any infiltration goes to the soil. If it is above field capacity, it's going to be drainage. So once we have the infiltration, depercolation, and evapotranspiration, which is simulated in the previous step, the DSAT model simulates the soil moisture content by subtracting the depercolation and the evapotranspiration data from infiltration data. Then we simulated the soil moisture content for the result. We simulated the soil moisture content using green beans model, and we observed that this model was able to accurately simulate the soil moisture content of green beans. The average mean absolute error for this model was 0.03 centimeter cube per centimeter cube during both periods. And this model performance was better in simulating higher and lower points, especially for 50% and 75% irrigation treatments. And we also use this model to simulate evapotranspiration of green beans. And we observed that this model was able to moderately simulate evapotranspiration of green beans during both periods. For instance, the mean absolute error during both periods were 1 millimeter per day, and the D-start was 0.53 calibration, and it was 0.06 during evaluation period, as you see on these figures. We also did the same thing for the sweet corn model. We simulated the soil moisture content using the sweet corn model, and we observed that this model was also able to accurately simulate soil moisture content of the sweet corn plants. And the average mean absolute error was 0.04 for the calibration, and it was 0.05 for evaluation period. However, the performance of this model was less than the green beans model in simulating soil moisture content. And we also used this model for simulating evapotranspiration, and we observed that this model was also able to moderately estimate soil moisture content during both periods, during calibration and evaluation periods. For instance, the average D-start was 0.6 during both periods, and the mean absolute error was 1.19 millimeter per day for calibration, and it was 1.09 during evaluation period. And this model performance in simulating evapotranspiration data was also less than the green beans model. And we also compared the cumulative daily simulated and measured evapotranspiration data, and we observed that there was a good agreement between the measured and the simulated cumulative evapotranspiration. However, we observed that the evaluation period performance was better than the calibration period, particularly for a sweet corn plot, as you see on this figure, had a good agreement compared to the green beans model. So as a conclusion, we have concluded that these two models demonstrated a satisfactory performance in simulating soil moisture content and evapotranspiration of green beans and sweet corn. So this model could be used as a useful tool in decision making related to agricultural water management that help us to optimize agricultural water use. So with that, I'll end chapter 3. So let's jump to chapter 4. So chapter 4 had two objectives. The first objective was to develop a deep learning regression method that could be used to simulate soil moisture content on several scales. And the second objective was to compare the performance of the deep learning model with the traditional machine learning models for simulating soil moisture content. So why we are interested to do these objectives, as I was mentioning before, soil moisture data are very important for efficient water management, but there are different ways to monitor soil moisture content. One of them is the traditional method, which we call it manual method. This method involves various steps, and these steps are very cumbersome and time and human labor consuming. But AI models can easily simulate soil moisture content using different weather parameters without involving all those steps that are involved in manual or other steps. So for this study, what we did, we used 15 minutes soil moisture, weather variable, soil temperature, and soil salinity data. And we removed all the missing and outliers from the target variable and input features. Then we developed deep learning regression network, and this deep learning regression network has 3 layers: input layer, hidden layers, and output layers. In this deep learning regression network, the input layer receives the data for processing, and the output layer generates the continuous prediction in our the soil moisture content. And the hidden layer is the most important layer in deep learning regression network, which transforms the input data through nonlinear operations. Then we also trained 5 machine learning models in this analysis. We use scikit-learn and TensorFlow for training the machine learning and deep learning models. In addition to that, we also use Hypergate and supercomputer computational resources for our analysis. So for the result, the first thing we did is we tried to see the correlation between the input features and the target variables. And we observed that the electrical conductivity had a strong correlation with the soil moisture content. For instance, the correlation coefficient for green beans dataset was 0.27, as you see on this figure 1 and figure 2. For the sweet corn, the correlation coefficient was 0.64. Then, after doing that, we evaluated the performance of the machine learning models, and we observed that the light gradient boosting model and the extreme gradient boosting model, as you see on figure 3 and figure 4, they were able to accurately simulate soil moisture content of green beans and sweet corn. For instance, for light gradient boosting model, the R square were 0.96 for green beans and it was 0.97 for sweet corn dataset. And we observed similar performance for the extreme gradient boosting model. And we also observed similar result for the SVM and Canyon models, where these 2 models were able to accurately simulate the soil moisture content of green beans and the sweet corn with a good accuracy. However, we didn't observe similar result for adaptive boosting model. This model performed better for green beans model than the green beans dataset than the sweet corn dataset. Then after evaluating the machine learning models, we compared the performance of the machine learning models with the deep learning models. And we observed that for the green beans datasets, the deep learning model was better than the machine learning models. However, for the sweet corn, we didn't observe similar scenario where the deep learning is better than all the machine learning models. In this case, the deep learning model was only better for 3 machine learning models, and it was less than 2 machine learning models. Those are the light gradient boosting model and the extreme gradient boosting model, but the performance of the deep learning model was better than the other 3 machine learning models. So as a conclusion, we concluded that this deep learning regression network outperformed most of the traditional machine learning model, showing a better accuracy on the enhanced erosion soil moisture prediction. So this deep learning, as well as the machine learning models, can improve the soil moisture prediction for the hydrological and the agricultural use. With that, I will end chapter 4. Chapter 5, we don't have result for this chapter, but the objective of this chapter was to evaluate the performance of canopy temperature-based stress indices and the spectral reflectance-based coefficient for evapotranspiration estimation. And why we are interested on this objective is in South Florida, as I was mentioning before, we have very difficult soil, and in addition to that, our weather is very variable. So any evapotranspiration estimation method, which depends on this fact that soil and weather might have some uncertainty. I'm not saying that it's good, but there may be some uncertainty. So we said why we don't try to evaluate plant physiological responses to water stress as evapotranspiration estimation method. So as a background, for instance, stomata help plants to cool by through transpiration. But when plants have a stress, what they do, they close their stomata. During that time, the plant canopy temperature goes up. So if we can able to see this canopy temperature variation, we can use this variation for modeling evapotranspiration. However, plants, they don't only respond for water stress in canopy temperature wise, they also alter the spectral reflectance of the plants. So if we can also see this spectral reflectance variation, we can use that for evapotranspiration modeling. So that's what we are trying to do here. So one of the crop water stress index, which depends on canopy temperature, the stress indices, we are planning this crop water stress index. We can calculate this crop water stress index either using theoretical method or empirical method. For theoretical method, we can measure all the canopy temperature for normal plant, the canopy temperature for stress plant and non-stress plant using drone image or IRT-based, ground-based IRT sensors, or we can also use empirical methods to calculate these three temperatures and then calculate the crop water stress index to calculate evapotranspiration. In addition to this crop water stress index, we are also planning to calculate canopy temperature ratio and operational simplified surface energy balance model to calculate evapotranspiration data of green beans and sweet corn. In addition to canopy temperature based stress indices, we are also planning to calculate spectral reflectance based proportion to calculate evapotranspiration. For instance, one of the index or proportion we are planning to calculate is vegetation indices based proportion. This proportion needs only NDVI value. Once we have the NDVI value, we can calculate the proportion, and by multiplying the proportion with difference evapotranspiration, we can calculate evapotranspiration. In addition to this proportion, we are also planning to use reflectance based proportion to calculate evapotranspiration for the green beans and the sweet corn. And for this chapter, we don't have result. I will to discuss here.